Thank you for kind introduction. Hello everyone, thanks for having me here. I'm pleased to give one of the last talks of this wonderful meeting, and although originally I was quite suffering from the fact that I have to wait till Friday, but then I realized that the very last talk, which will be given by Sebastian, will be full of tough and wonderful mathematics, certainly. So I've decided that my talk can be slightly more relaxed from this point of view, so you can again look forward some nice, but this time also ugly pictures in my talk. So I will start with my favorite industrial application, which brought me into the field of diffuse interface modeling. Then we will briefly touch derivation of diffuse interface models, although we have already seen something in the previous lectures. And in the last part of my talk, I will show you some results of my computer simulations. So, as most of you already know, this is my favorite industrial application, the float glass process, or the Pilkington process. Yeah, although after all those years I could say that I hate it, but I still like it because it is an ingenious technology for manufacturing flat glass on industrial scales. I mean, tons of flat glass per day. And it was invented in 50s last century, and it has not been touched since that time, basically. So it brings a natural question if the process is somehow optimal, and not surprisingly, mathematics can help us to find this out. So, for those of you who haven't seen this figure yet, let me explain to you what is on it. So here you can see, you can see a schematic diagram of the manufacturing line for float glass process. So here is the melting furnace. Molten glass comes from this furnace, and it is put on top of molten tin. So this is the tin bath, which is held in a chemically controlled atmosphere. And the only thing you need to do is that you have to cool down this somehow, because the glass floats on tin. It makes perfectly flat surface, and you want to cool it down while keeping this structure. So this gives me a chance to play this wonderful animation once again. I have to apologize that I do not have newer version, but believe me, this was like thousands of clicking in ParaView, and I don't want to do it again right now. So here is the glass coming from the furnace. It goes down along this lip, and it floats on top of this tin bath, and it continues floating. So our modeling approach this is of course only the beginning of the manufacturing line, which is in fact much longer, and our modeling approach is to somehow split the process into the two parts. So I'm responsible for this one, which can be basically considered to be isothermal in the first approach, because the temperature is supposed not to vary too much. Here, the other part, if you are interested in the modeling approach applied there, you can ask, for example, Jan Blechta, who is in the audience, or Vít. But we will focus in this talk on this first part. So you have probably noticed that it is a quite complex free surface flows, which can be generally classified as a multi-phase flow, since it is a simultaneous flow of materials with different chemical properties but in the same state or phase, so the liquid phase in this case. And this is of course the phenomena which occurs not only in the glass industry but also in other industrial applications. So to be more specific, so our target setting is this one. We want to describe several immiscible, incompressible fluids in a fixed domain. And to achieve this, you have basically two possibilities how to do it. So one modeling approach is a sharp interface approach, which has the advantage that the derivation of the governing equations is somehow intuitive if you know how to specify the jump across the sharp interface. But from the implementation point of view, you need to take care about explicit interface tracking. On the other hand, in the diffuse interface approach, this interface between the fluids is supposed to be of finite thickness, within which, so it's a transitional layer within which the components, the fluids, can mix, but otherwise they tend to keep separated. So in this case, the interface tracking is somehow implicit, and but the price to pay is that you need very fine mesh to describe the interface dynamic properly, because you need to capture the steep gradients across the interface. So there are plenty of diffuse interface models. The situation is quite clear in the less interesting case of matching material densities. So the widely accepted model for this is so-called model H, which was derived by Hohenberg and Halperin. But for us, for the case which is interesting for us, the situation is more complete. You have basically a jungle of models here. So I wanted to provide some uniform framework for derivation of different models. And we will discuss this in the modeling part of this talk. So this was the theoretical issue that is encountered when you are using diffuse interface models. The practical issues are even more serious, because what you usually see if you want to do simulations with real parameter values, like these are the approximate values for glass, tin, and atmosphere. I mean, this is the density, and these are the values of dynamic viscosities. So you can see that there is a high density ratio, and also you need to overcome the problem with small viscosities. And this is the reason why you can see here in this ugly figure the spurious velocities close to the interface. We will discuss this at the end of the talk. Then the other issue is that to be able to do 3D simulations, you need to come up with efficient numerical algorithms. So we also did some steps in this direction with Jan, who had a poster here on PCD preconditioning, which was the idea we have noticed for the first time in this paper by Kay and Wellford, who applied this technique in the context of Cahn-Hilliard-Navier-Stokes fluids. And last but not least, then there are some other issues. For example, you need to think about what one should prescribe at this artificial boundary where we have decided to cut the domain. So I don't know if Michal Bátor is still here, but if you would like to add like a third column to your poster about do-nothing condition for multiphase flows, I would be grateful. And so let me explain to you what I mean by uniform framework for derivation of various diffuse interface models. So in order to describe your physical systems, you have several possibilities to choose your phase field variables. So in our case, we will always assume that the system as a whole satisfies so-called mass additivity constraint, And one possible candidate for order parameter is then concentration of individual phase, or concentrations of individual phases. The other possible choice would be porosities or volume fractions, which are especially appropriate if you have a system in which you can assume that it also satisfies volume additivity constraint. Other possible choice would be, for example, to use partial densities. So the fundamental assumption for us is the assumption of co-occupancy, which is traditionally accepted in the theory of mixtures. So you can think that at each point of your domain you can feel the contribution of all the phases. Based on this assumption, you can write your balance equations for individual components. So here is the balance of mass for the ith constituent. So you can see partial density here and also partial velocities here. So let me now introduce some averaged velocity v for the mixture as a whole. So then we can formally rewrite this first equation into this form with v, supposing that we can introduce so-called diffusive mass flux, which is the quantity that at the end of the day has to be determined by some appropriate constitutive assumption. You can rewrite it using material time derivative. And this same equation can be expressed also in terms of mass and volume fractions, where this J with tilde is now the diffusive volume flux because it is divided by the material density. If you sum up these two equations, you will end with a balance of mass for the mixture as a whole. And now it is the right moment in which we want to specify what is our average velocity. So traditionally accepted choices are mass average velocity or barycentric velocity, which leads to this fact that with Vm, this capital J, which is the sum of diffusive mass fluxes, vanishes. But for the case of generally non-matching material densities, the other J with tilde do not vanish. So barycentric velocity field in this general case is not solenoidal. The other choice is the volume averaged velocity, and this leads to opposite relations. So in this case we have solenoidal velocity field, but we have something in the general case on the right hand side of this equation. You can do the same business with other balances for momentum, angular momentum, total energy and entropy. So you have balances on the level of individual constituents. You can and when you sum up these equations, you will have their counterparts for the mixture as a whole. So this is in the case with barycentric velocity field, and it is good because it resembles the governing equations for a single continuum. The situation is much worse in the case with volume averaged velocity, because then you have some problematic terms in your governing equations. And typically what you need here, you need to have also the evolution equations for this capital J, and this can be obtained by specifying interaction terms in your balances for individual constituents. But this is usually a tricky business. So, but we will assume for now, or I can tell you right now that in order to proceed further in this case, we will need to do some approximations, and we will need to neglect some terms about which we cannot a priori say if they are they have some influence or if they don't. So now we have the balance equations, and the question for us with respect to the application of our interest is what we should do in order to keep the phases separated. We don't observe the mixing, because this situation also describes general mixtures. So with suitable choice of constitutive assumption for the free energy, which typically for two phases is the double well potential with two local minima. So we will use porosities in our description. So we have 0 and 1 here and two local minima. And this basically ensures that the phases tends to keep separated. So we have balance equations. Maybe we have also interaction terms. We have free energy constitutive assumption. So in some sense, we have a complete description. But do we really need a sledgehammer to crack a nut? So this is the point where this talk is related to this meeting. So we can do some model reduction. We want to neglect some less important interaction terms, which may be difficult to decide. And we want to reduce the number of governing equations. So we want to work only with balance of mass for individual components and other balances for the mixture as a whole. So based on the ideas from this paper, we have now two options. So either I will bother you with the identification of entropy production, or we will use my favorite thermodynamic grinder. We will do several rotations, and we will end up with the system of partial differential equations for unknown quantities, which are field variables, velocity, and pressure in this case, because we have used the grinder in the isothermal setting. So this model in fact contains two settings which I have encountered in the literature. One with this red term here, with this diffusive flux in the balance of a linear momentum, comes from Helmut Abels, Garke, and Green. And the model with this term being neglected corresponds to the model derived by Boer and Lapuerta. You can notice here that we have a single parameter, epsilon, with which we control the interface thickness in the model. So this is the model based on the usage of volume average velocity, which is solenoidal here. The other possibility is to use barycentric velocity, but then the model is more complicated as the velocity field is not solenoidal, and we have also somehow the stronger coupling between this Cahn-Héliard and Navier-Stokes parts, because now we have pressure appearing here in this equation. So here comes the possible extension for us. So how about using this grinder in an isothermal setting? In such a case, it is possible to derive the evolution equation for the temperature, but the crucial task here is how we should modify this double well potential in the non-isothermal case and be still somehow close to our target application, because this model was originally derived for different purpose, right? It was this assumption was used to describe phase separation, but we want our phases to be separated for all temperatures. Okay, so this is something which should appear in my PhD thesis, and now we can come to computer simulations. So not only that we have plenty of possible models, but now we have also plenty of possibilities how to discretize the equations. So for space discretization, we use finite element methods. Discretization in time is more subtle, so this would be the straightforward approach to do the discretization for the system as a monolithic system. But this is of course very nonlinear, highly nonlinear problem, and this scheme will not be affected. So it's just like a toy scheme. The other possibility is to do decoupling for Cahn-Hilliard and Navier-Stokes parts, which was described in this paper by Minjot, where you can find also the proof that this scheme is in fact energetically stable. Or recently, I have discovered the paper by Dong, who continues the decoupling, and he uses projection method for resolution of Navier-Stokes equations. So, extensive testing of various models and discretization schemes is required, and for this purpose we need an appropriate tool. So in our case we decided to use Phoenix because it offers automated code generation, so also fast prototyping of the models and various schemes. As a side product of my thesis, I'm working on the development of Mouflon package, which is a package for multi-phase flow simulations. And it is based on top of Phoenix. And now I will show you some work which has been done on this package. So first of all, we want to do convergence tests for our different discretization schemes. So this is our manufactured solution, and we want to test the numerical solution against this one. So these are the results recovered from this paper by Dong. You can see that the scheme which he proposed is second order in time, which is good. These are the results for monolithic scheme, which seems to be also of the second order with some special treatment of time stepping, and it seems to be somehow more precise in space if you use high element order. These are the results for the semi-decoupled scheme designed by Minjot. This scheme is only first order in time, and because of that not very accurate in space, but still it is my favorite scheme because it seems to be most robust. Then the other possibility which is contained in this Mouflon package is to do some other benchmarks, like this classical example for bubble. With Jan, we did this. We are working on the development of the package for preconditioning of Navier-Stokes, and the idea is to couple the two packages together. And then I wanted to show you something about the spurious velocities for real materials parameters, but I think the time is gone, so maybe some next time. Thank you for your attention.
Thank you very much for your talk. I believe we still have time for questions, if any.
Maybe Martin can show this as the question.
Okay, maybe you can show.
Okay. So for quite some time we were not sure if the oscillations which appear on the interface. So this is a situation where you have a stable interface between, let's say, air and water, and what we exactly observe here are some spurious velocities, and we have not been sure if this comes from the model or if it is the matter of discretization, but now it seems that it is really the matter of discretization, because I was able to recover these spurious velocities only by solving the stationary Stokes problem with variable density and viscosity. So the high density ratio in this case and small viscosities are responsible for no, I mean, the thing is that the variation in the density causes the troubles, and it's because, and the clue now I'm still working on it, but it seems that if you use higher order finite element approximation for pressure, you can somehow suppress these oscillations. So it's kind of a brute force, but it could be used to some extent.
Okay, so since we are a bit short of time, let's thank the speaker again.